Okay, so these next couple of slides, I'm going to include the next two in this one video. But these are conceptual examples about really showing the importance of the relationship between the frictional force being proportional to the normal force. Okay, so friction is proportional to N. Luggage on a car, like surfboards and so forth, are often strapped down on that car from ropes that sort of go from passenger to driver's side. They go sort of left to right. But the amount of air resistance that's acting usually flows from front to back. So the cargo is very likely to be blown sort of backward off the car, and yet we're using ropes that are attached left to right to be able to prevent that from being blown off. How's that work? Why do we do that? The idea behind this is that those straps are going to exert downward force. So if I consider this to be the weight of the cargo, I'm going to add some additional normal force by strapping that cargo down. So these are from the straps. So I'm exerting downward force there. Now that downward force means that the actual normal force will become larger. So that normal force is not equal to the weight here. It's actually quite a bit larger now. Since I have a larger normal force, I have a greater amount of static frictional force that will keep that thing from blowing off of that car. Now, if this is trying to push the surfboard towards the left, the static frictional force, let me draw that here, this would be the force that the air is trying to exert. Well, the static frictional force can now become bigger simply because I have a larger normal force. So this static frictional force becomes larger. Right? These two things are related through the value of mu. Okay? So if I can make N bigger, I make Fs max bigger, and that's going to keep that thing securely fixed to the top of my car. Linemen are often told, for blocking, they're often told to go into the opponent and then lift up a little bit. What's happening there, the reason we have them do that, is that the weight of that opponent would have a typical normal force acting on them as well, which would be equal. But if I start to lift up on that person, so this is the force from the lineman, that's going to reduce the amount of normal force acting there. So the normal force acting on that lineman will become smaller because I'm lifting them up. Since the frictional force is a portion of the normal force, I'm going to have less static friction acting on that opponent, which means that I'm more easily able to move them around. Now, this one down here is a little bit harder to see just on this particular static diagram here, but you can find the center of gravity on any object here by sort of sliding your hands in. As you try this, and we do this in class, you'll see that the hand that moves as you start to move inward, apply pressure with both hands, the hand that moves is the one that has the least amount of frictional force that's acting, and that has to do with how the weight of that bar is being supported by those two fingers. What you'll see is that those fingers will each move in at different rates until they sort of move together and find the center of gravity at one spot. And so hopefully you've had a chance to try that in class. Again, sort of difficult to see on a static diagram. Now, the last example I want to look at conceptually is about which of these two situations would be easier to sort of move your sister along on a sled. Let's say you have a little sister. She wants to ride on her sled. You're going to be pushing her or pulling her on flat ground. Will you exert less force if you push her like this or if you pull her like this? Okay, and in either case, we're going to sort of exert a force downward relative to the horizontal or upward relative to the horizontal. So the same angle in either case. So in which of these cases would you exert less force? So we're going to start by drawing an FBD. So the weight of my sister always stays the same. That's how hard the earth is pulling on my sister. And so regardless of what I'm doing, the weight of my sister would be the same. So those two weight forces would be identical. Now when I go to push down at an angle, let's go ahead and represent that force here. When I go and push down at an angle, I'm going to draw that with a value f. I don't know how big that is, really. It's just sort of a conceptual example. That angle here is theta. Well, when I push down at an angle like this, what that does to the normal force is it actually increases it. Right? The normal force becomes bigger than the weight. And the reason for that is that the normal force, again, sort of responds to all the forces that are acting vertically. Well, the Earth is pulling down, and I'm also pushing down with at least a portion of that force is pushing down. The normal force will grow in response to the vertical component of that applied force. Now, the frictional force here is, again, a proportion of this. Well, it may not be very large a proportion since it's on snow, but the greater the normal force is, the bigger that frictional force. Okay? Now, if this is moving at a constant velocity, which is probably the case, then the horizontal component of the applied force would exactly balance the frictional force that's opposing that motion, and the normal force would exactly balance the downward forces here. I would have to exert a decent amount of force to move them along at constant velocity. Now let's consider what happens when I take my sister and start pulling her towards the right using a force that's at an angle upward. Now I am going to draw this smaller, and you'll see why here in a moment. If that's the angle that I'm pulling horizontal or at an angle, if that's the force that I'm pulling at an angle, I will see that the normal force will actually become smaller here because I have a vertical component that's helping sort of balance my weight. I don't have to have the ground push up with me with as much force. So the normal force here becomes smaller than it is here. Now, if the normal force is smaller, then I'm going to also have less frictional force. So F sub k will be smaller. And again, for the same basic idea, if I'm going to move at a constant velocity, the horizontal component here only needs to be as big as the kinetic frictional force. It would be far easier to pull my sister than it is to push my sister. Again, how the frictional force depends on the normal force is a pretty important part of the way friction sort of acts.